Okay, welcome to Math E102, Great Expectations. I'm going to be talking this week almost entirely about the expectation of a random variable. Next week I'll move on to some more subtle, closely related topics like conditional expectation. There's going to be a quiz 2 weeks from tonight, but it will cover only tonight's outline. I am hoping that next week's material will be useful background for the quiz, but I will not devise quiz questions that are based primarily on stuff that comes up next week. So we're ready to begin. I'll start in green and we can change colors. And what I want to begin with is the definition of the expectation of a random variable. And then I want to walk through a bunch of familiar examples where the mass functions may have looked kind of messy and implausible, but when you compute the expectation, you have strong reason to believe you've got everything right. So here's the definition of expectation. It gives you another chance to use a fancy letter. There's a fancy E. It's the expectation of a random variable. And it really is, as the notation suggests, a function. It assigns a number to a random variable, and here's how it does it. You take every value that can be assumed by the random variable and multiply that value by the probability that the random variable achieves that particular value. And this is what you've been doing all your life under the guise of averaging. The only difference between expectation and average, in my opinion, is that average is the appropriate term when you're dealing with actual data. 40 people got 70% on the exam, 40 people got 90%, what was the average grade, as opposed to the probability that you will get 70 on the exam is 50%. The probability that you will get 90% is 50%. What's your expected grade? But the calculation is the same. Just multiply the value by either the actual fraction of cases where something occurs or the probability. So, example 1. We'll go back and do Chuck-a-Luck. Remember Chuck-a-Luck? This is the carnival game where you roll 3 dice, you pick your special number, and what I'm going to do is assume the special number is a 6. So x equals the number of 6s that you roll on 3 dice. And now to apply this formula, I'm going to make a table of all the values that the random variable capital X can achieve, namely 0, 1, 2, and 3. I'm going to calculate very quickly the probability that the random variable achieves that value, and then in the right-hand column, I'm going to compute the product, and I'll add it all up. Probably work pretty well in a spreadsheet. Okay, x equals 0 and x equals 3 are easy as long as you can cube integers in your head. In order to get no 6s, you have to be unlucky to the tune of 5/6 on each die. And with 3 independent dice, you'll get 5/6 cubed, which is 125 over 216. And this is the result that I got in one of the very earliest classes, showing that you were more likely to lose than to win at this game. If x equals 3, things are also pretty easy. You've got to roll a 6 on each of 3 dice, so the probability of that is 1 in 216. The other 2, I will remind you how to do the counting. In order to get 1 6 and 2 other things, you need a situation like this. And the way the counting goes is as follows. The 6 can show up on any one of the 3 dice. That's a factor of 3. And then on the other 2 dice, any pair of the numbers 1 through 5 inclusive can show up. There are 25 possible pairs, and therefore, in this case, out of the 216 ways that 3 dice can turn up, 75 are of this sort. Probability 75 and 216. And the calculation's similar for getting 2 6s, only it's easier. The number that's not a 6 can show up on any of the 3 dice. That's a factor of 3, and there are 5 possible values for it. So that's 15 out of 216. And never calculate all the values of a mass function and neglect to check that they sum to 1. If they don't sum to 1, you've done something wrong. Okay, now I'm going to compute the expectation. Yes?
Oh, the 75 is just 5 squared.
The 75 is 5 squared times 3.
Times 3.
Yeah.
Right.
There's a 3 for this and a 5 squared for that.
Right.
Whereas here there's a 3 and a 5 associated with the same thing. Okay, so nothing from here, of course. 1 times this probability. 2 times the probability of getting 2 6s. 3 times the probability of getting 3 6s. And you add them all up, you get 108 over 216, which is a half. And I think that this is the reasoning that most people engage in that tempts them to play this game. They correctly perceive that with 3 dice, the expected number of 6s must be 1/2, namely 1/6 for each die, and there are 3 of them. And they jump to the conclusion that this is a fair game, forgetting that the rules of the game only pay you off as if you got 1, even in the case where you got 2 or 3 6s on your dice. So that's chock-a-block. I'll clear this and do my next one. The next one involves the number of spades you get if you pick a pair of cards out of a deck. And while the make-up quizzes were by and large quite good, a number of people were still getting this wrong, so I think there's no harm in doing one more example. So this time my random variable x is equal to the number of spades in a pair from the deck. And we might as well be organized again. Enumerate all the values of x and work out the probabilities, 0, 1, and 2 in this case. Okay, I want someone to give me a product of 2 fractions that says the probability that if you pick 2 cards out of the deck, no replacement here, you choose one of the 52 cards at random and then another of the remaining 51 at random, what's the probability of getting 0 spades? The first factor is easy. 3/4. Okay. So now you got 1 non-spade out of the deck. What's the next factor?
12 over 51.
Non-spade.
Non-spade. Excuse me, 36. Did the subtraction in my head. You know what I mean.
Yeah, I know what you mean.
The number of non-spades.
The number of non-spades over the number of cards. There are now 38 non-spades left and 51 cards left. And when I multiplied that out, it came to 19/34. Let's do the other moderately easy one. Getting 2 spades. What's the first factor?
1/4.
1/4 for getting a spade on your first card. Okay, now you've taken 1 spade out of the deck. So on the second card, what's the probability of getting your second spade?
12/51.
12 over 51. And in fact, let me remind you that what we're doing here, I couldn't say this when we first introduced this, is that P, A intersect B, where A is first card as a spade and B is second card of the spade, we're really calculating the probability of A times the probability of B given A. These are not independent events. In order to calculate the probability of their intersection, you have to calculate the probability of the first event, and then in that change situation, calculate the probability of the second event. Okay, this one, when I worked it out, I believe I've got these right because they sum to 1. This came out to 2 over 34. Now, I could add these up and subtract from 1, but I'm going to play it safe and do the 1 spade. What's the probability that you get a spade followed by a non-spade?
3/4.
1/4 for the spade times
38.
Careful now. You've taken a spade out of the deck. How many non-spades remain?
39.
All 39 of them. Now, why is that the wrong answer for this value of the mass function?
Come up with why if you pick a non-spade first.
They could have come up in the other order, exactly. So I've got to multiply by 2, and when I multiply by 2, I get an answer that simplifies to 13/34. Now, this is a mess. It does add to 1. But what does the expected number of spades have to be? You pull 2 cards from a deck. What's the expected number of spades?
1/2.
1/2, sure. Because each time you pull a card, the expected number of spades is 1/4. You got 1/4 chance of getting 1 spade and 3/4 chance of getting no spades. And as I'll prove in a minute, when you add random variables together, you add your expectations. So it will turn out, in a lot of cases, we'll be able to calculate expectations of random variables, even though calculating the whole mass function like this would be an absolute nightmare. Okay, let's check this one. 0 from here, 13/34 from here, and now I've got to multiply this one by 2 because we got 2 spades, so the expected number of spades is 17/34, which is 1/2. Wow. Okay, one more. Let's go back and do Munchkins. And this time, let's start by figuring out what the answer has to be and then get it. The deal, as usual, is there are 6 Munchkins in the bag, and 2 of them are chocolate. Thomas gets 3 of the Munchkins, namely half the Munchkins. What's his expectation for the random variable x, which is the number of chocolate Munchkins? If there are 6, including 2 chocolate ones, and he gets half the Munchkins, what's his expected number of chocolate Munchkins? It has to be 1. Okay? Let's try this. X equals the number of Munchkins, and the deal is 2 of 6 are chocolate, and Thomas gets 3. Again, this is a somewhat non-trivial calculation of a mass function, and the fact that we can pretty much guess what the expectation has to be gives us a nice check. So Thomas gets no Munchkins. I'll remind you how to do this. He gets 3 plain. His sister gets 2 chocolates and a plain. There are 4 ways this can happen because his sister can get any of the 4 chocolate Munchkins. So you have 4 out of the 20 possible ways of choosing Munchkins for him. That's 1/5. In the case where he gets 1, you can argue that there are 2 ways of choosing the chocolate Munchkin that he gets. There are 4 choose 2 ways of choosing the 2 plain Munchkins that he gets. and that comes out to 3/5, and the last one comes out to 1/5 again. So when we do the expectation, we have nothing from there, 3/5 from there, 2/5 from there, and we get 5/5, which is equal to 1. I'm going to do one last example that I didn't mention in the outline. I didn't mention it in the outline because I actually put it as a homework problem, but this is such a standard calculation that I thought I'd make sure that everyone had seen it. This will start you off on the homework problem where you're actually asked to count spams per hour in your inbox and see whether it is nicely modeled by a Poisson distribution, as I would expect it should be if the spam arrives randomly. This was one random occurrence, I thought, where we all, alas, have enough statistics so that we can probably check a hypothesis. So, the other reason I want to do Poisson is I've said here sum over all the values that x can achieve. In the previous cases, there have only been a finite set of such values. Here's a case where there's an infinite set of such values, and I'll have to do an infinite sum. Either at the end of tonight's lecture or at the very beginning of next week's lecture, I will talk about a carefully contrived case where doing this sum is invalid because of a conditionally convergent series. I know Dana's been waiting to hear about that. But for tonight, the sum is going to be the sum for the exponential series, and we know that that was legitimate. So here's the mass function for the Poisson distribution. The important part is it's this parameter lambda raised to the x power divided by x factorial, but this doesn't sum to 1 in its current form, so I have to put e to the minus lambda outside just in order to make the probability sum to 1. To compute the expectation, all I have to do is multiply this mass function by x and sum over all the possible values of the variable. And I'm going to do something slightly clever and often useful. I'm going to write the sum as going from 1 to infinity on the grounds that when x equals 0, this x in the numerator will kill the term off. Now, alas, a lot of these expectation problems boil down to tricks in series summing. That is, you write down the formula, and then the entire rest of the problem is figuring out some clever change of index that lets you sum the series. And you build up your mathematical cleverness, but you don't really learn that much more about probability. In this particular case, the result is worth memorizing, and so I don't mind spending some time on the trickery. I can pull out my e to the minus lambda. I've got the sum from x equals 1 to infinity of, well, what should I write in the denominator? X minus 1 factorial. And it would really be nice to have a lambda to the x minus 1 factorial in the numerator. I can do that. I've got lambda times lambda to the x minus 1. Okay, now I've got the sum of lambda to the x minus 1 over x minus 1 factorial from x equals 1 to infinity. That's the sum that defines the exponential function. It would be a nice idea to set y equal to x minus 1. So what have I got? I've got lambda times e to the minus lambda times the sum. If x goes from 1 to infinity and y is x minus 1, y goes from 0 to infinity, lambda to the y over y factorial. This whole business is e to the lambda. That cancels that. And there's my answer. So this is a very useful thing to know about the Poisson distribution. the expectation of the Poisson distribution is this parameter lambda, and this is very usefully employed in the opposite direction. If you hypothesize that the number of spams per hour in your inbox, which is a random variable, of course, obeys a Poisson distribution, you need a value for lambda. All you have to do is calculate the expectation of the number of spams in your box. Now, strictly speaking with that, you should do what I did last night when we got back from a weekend in the Adirondacks. I said to my wife, I bet we've got 176 spams in our inbox. That's really talking about expectation. And then what I did was I actually went and looked in my inbox. I counted up the spams divided by the number of hours. That's the actual number of spams per hour. And what statisticians do all the time is look at real-world data and use the real-world data to estimate the parameters for probability distributions. So a good guess for the parameter would be the number of spams you get over some period divided by the number of hours. That may not be the correct value, but I'm going to be able to prove toward the end of the course that if you wait a long, long time, if you say, I've counted spams for 9 months and I have reason to believe that this parameter hasn't changed, then the probability that such an estimate will be bad gets very, very, very small. Yeah, sure. Okay, so what I did, Sue, was I made the change of index y equals x minus 1. So I replace x equals 1 by y equals 0. X minus 1 factorial changes into y factorial. Lambda to the x minus 1 changes into lambda to the y. And I pull this one outside here. And then I said, this is our definition of e to the lambda. This is what we mean by e to the lambda. And since we proved that the laws of exponents hold for the exponential function, e to the lambda times e to the minus lambda is e to the 0 or 1. Fair enough? So the answer is lambda. Yeah. Okay. Now we're going to move along to topic number 2. This is a theorem with a wonderful name that, for some reason, doesn't show up in our textbook. The book that I use in my other course that Sturzacher co-authored called it by its standard name, which is the law of the unconscious statistician. So I've titled this section Unconscious Statistician. And I think the reason it got this name is that this is a provable theorem, but the formula is so obvious that most people who use it probably believe it's a definition. They don't realize that it's something that ought to be proved. So I'm going to prove the law of the unconscious statistician and then show you with a simple example that calculations done using this law are somewhat different, though they yield the same result, when compared with calculations using the actual definition of expectation. So we've now got number 2, unconscious statistician. Okay, here's what's going on. We have one random variable that's a function of another random variable, y equals g of x. And in the example I'm going to do, the random variable x is the number by which the counted number of visitors entering a museum exceeds the number that exited that museum. You know, you walk into a museum, there's always this person here going click, 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 click. And I've often wondered, what do they do at the end of the day if 753 people were counted going into the museum and only 752 were counted coming out? Do they say, there's someone hiding out in the museum, we can't close up for the night unless we search for them? I think they say, well, it's hard to count accurately. That happens. But being too high or too low probably doesn't make any difference, and so a reasonable thing to do is to square the error. So the function I'm going to use is just the squaring function. That will be my g of x in the example. Here's the formula. The formula says this. If you want to compute the expectation of a random variable y, all you do is take all the values that x can achieve. You take the probability that x achieves that value and then multiply by your function. So what this will say is take all the values of x, square them in my example, and weight each value of x squared by the probability that the value of x that gives rise to it occurs. That's a correct calculation, but it's not exactly what the definition of expectation tells you to do. So here's the proof. If we want to calculate the expectation of y according to the definition of expectation, we're supposed to do our sum over all the values that can be achieved by y. Those will only be positive values if y is the square of x. And what we're supposed to do in each case is to take the appropriate value of y and weight it by the probability that the random variable y achieves that value. So far, so good? And now another way to write this, consistent with the book's notation, is I will sum over all the different values of y. I'll call them y1, y2, and so on, represent them generically by yj. And then to calculate this probability, what I have to do is take the mass function for x and sum it over, it should be a lowercase x, and sum it over all the values for which the function g, my squaring function, gives the appropriate value of y. This looks profound, but as I think you'll see when I do the example, it's absolutely trivial. Now let's figure out what this works out to. So I'm summing over this index j, and now for each value of x, the value of y that's achieved is g of x So all I've done here is to say I can multiply by the value of y before I sum. Okay, now tell me, if I run through all the values of y that can be achieved, and for each of them I run through all the values of x that lead to that value of y, what's a simpler way of stating what I'm summing over? I'm taking every possible value of y, and for each value of y, I'm summing over all the x's that lead to that value of y. What am I doing with regard to the values of x? I'm summing over all of them, right? I'm breaking them down according to the value of y that they lead to, but I'm including each of them once and only once. So this is the sum over all the values of x of the value of y that x leads to, g of x, multiplied by f of x. And that's the proof, and it's a hard proof to follow because the result is so obvious that it's not clear exactly what had to be proved. So here's my example. I think I'm going to try to sneak it on the board here. So my random variable is the number of excess patrons entering a museum in one day, and I'm going to assume my guards are pretty good with their counters, and they're never more than 2 off, and the probability that this random variable achieves the specified value is respectively 0.05, 0.1, 0.5, 0.2, and 0.15. Now, g of x is the squaring function. The value of y that arises for each of these is respectively 4, 1, 0, 1, and 4. This might be a measure of how bad a museum guard is at counting. And now I can use this formula. If I use this formula, it tells me to proceed as follows. It says to take g of x, which is x squared, times the probability that x achieves that value, which means 4 times 0.05 for 0.2, 1 times 0.1 for 0.1, 1 times 0.2 for 0.2, and 4 times 0.15 for 0.6, and add them all up to get 1.1 as the expectation of x squared. So that's what the law of the unconscious statistician says to do, and it's nice because we can work straight from this table. But that's not what the definition of the expectation of y says to do. How many different values can y achieve? Just 3, 0, 1, and 4. So the definition, which is here, says I should do the calculation slightly differently. It says I should take the value 0 and multiply it by the probability of 0, and then add on 1 times the probability of achieving the value 1, which is 0.1 plus 0.2. And finally, I should take the third value that can be achieved by y, namely 4, and multiply that by 0.2 plus 0.6. And when I do that, of course, I get 1.1. And you say, there's absolutely nothing to this. You're adding up the same set of terms. Look, you got a 0.1, a 0.2. Wait a minute. Sorry, I made a mistake. I did my multiplication prematurely. This is, it's 0.05 plus 0.15. So, if you compare the different terms, that matches that, that matches that, that matches that, that matches that, that matches that. Nonetheless, it will turn out that this way of calculating expectation is the first step in most of the proofs I'm going to be doing. So we're going to need this rather trivial result before we can move on, which I propose to do right now. We're going on now to number 3, which is properties of expectation. In the textbook, these are proved rather fussily. And the reason that they're proved rather fussily is that Sturzacher always has in the back of his mind the danger that there might be an infinite number of possible values for x, and that the resulting infinite series isn't absolutely convergent. So he always says, first we have to show absolute convergence. Phooey on that for tonight. Next week I will talk about it when it's interesting, because you can see how something might go wrong. But I'm going to do this under the assumption that any time I have an infinite sum, it converges nicely. And if for this week you want to think about this just in the finite case where there are absolutely no potential problems, that's fine. So here we go with number 3, properties. I'm going to do these in a slightly different order than they're done in the book because I can use one of them to help with a later one by doing this. The most important of these properties I would characterize by the statement that expectation is a linear operation. And I'll show you what I mean by that. I'm now going to start with a random variable capital X and do something rather messy to it. I'm going to evaluate the function g on it, multiply by a, and then evaluate the function h on it, and multiply by b. But this is a perfectly reasonable operation. This might be something like x is the number of sixes you roll at Chuck-a-Luck, and your payoff is 2 times the sine of x plus 3 times the exponential of minus x. So there's nothing particularly profound to this. And what I want to show you is that basically I can move this expectation inside, and here's how I'm going to prove it. Let's say, law of the unconscious statistician says all I have to do is take the mass function for this. That's f of x. I warned you last week that sometimes I will not subscript this. There's only one named random variable around, namely capital X. So this is the mass function for the random variable capital X. And then I multiply this by a times g of x plus b times h of x. Now, this has nothing to do whatever with probability theory anymore. This is just basic math. It's a summation. And I can write this as a times the sum of f of x, g of x, plus b times the sum of f of x, h of x. That's a times the expectation of g of x, and now I want a capital letter in there again, plus b times the expectation of h of x. Just what you would have guessed, mind you, but notice if I tried to go back to the definition of expectation, it would have said, first you have to figure out all the values that can be achieved by a times g of x plus b times h of x, and then you have to compute the probability for each of them, and then you can use the definition of expectation. So it's very important to us to have this shortcut technique for calculating expectation. Okay, that's the first one. The second one is really trivial. This is a random variable that really isn't worthy of the name random. But it's entirely reasonable to have a random variable that assigns the specific value b to each outcome. Okay. This assigns to each murder mystery the number 17. And what I'm going to tell you is that the expectation of a random variable like this is the value b, because to get the expectation, we have to sum over all the possible values of the random variable x. There's only one of them, it's b. Multiply each by its probability, in this case 1, and you get b. So that's reassuring. If a random variable is guaranteed to have the value b, its expectation is that value. The third one is a special case of A, and in fact I stated it a little sloppily in the outline. What I said in the outline is correct, but I'm going to simplify a little more. So in part A, I'm going to choose for g of x the identity function, and for h of x the function that has the constant value 1, and that tells me that the expectation of A times X plus B is A times the expectation of X plus the expectation of B, which we now know is B. So this says, in the special case where you have a linear function of a random variable, all you have to do is take this coefficient times its expectation and then add on the constant B. It's hard to see how anything else could have been true, but now we prove it. And finally, the last one is, again, one of these reasonable things. If you enter a lottery where you're told, this ticket is guaranteed to pay you at least $5 and it's guaranteed to pay you no more than $20, you say to yourself, well, my expectation from owning this lottery ticket and being about to scratch it is somewhere between $5 and $20. It can't lie outside that range. And the proof for this is fairly trivial too. I'm going to assume that the random variable A is greater than X and no greater than B. And I can certainly therefore say that A times the mass function f of x is less than x times the mass function f of x is less than or equal to b times the mass function f of x. Because for every value of x for which f of x is different from 0, a is less than x is less than b. There are other values of x for which this doesn't hold, but for all those values, the mass function f of x is 0, so it doesn't make any difference. Now I'm going to sum over all these. Okay? A is a constant. The sum of f of x over all possible values of x is 1. This is, by definition, the expectation of the random variable capital X. And here again, the sum over the f of x's is 1. So if a random variable is guaranteed to be in the range between a and b, so is its expectation. So far, so good? Now, let's see if we can actually calculate the expectation for a random variable described by a formula. So I'm going on to number 4 now, which is called binomial expectation. This is a really good marker, isn't it? Either that or a really good eraser. And while my general theme is going to be, don't try to compute these things by summing series, compute these things by using the fact just proved that the expectation of the sum of two random variables is the sum of their expectations, I decided it was so easy to prove this one by brute force that I'm going to show you how to do it. Though I promised, having been burned last spring by putting things like this on the quiz, I will stay away from this sort of calculation on the quiz, because basically some people are really good at changing indices in series and others are not, and there's not much you can do about this after someone is about 8 years old and you're not really testing what you're teaching in your course. So you may like this, you may not. That's a matter of taste. You may be good at it, you may not be good. In most endeavors in life, that doesn't really matter. I personally think it's lots of fun. I love to sum series, but I won't inflict too much of it on you. Okay, we got a binomial distribution. We flip n coins, and we want a mass function, which is the probability that we get I heads in n coins. So this will be flip n coins with the probability of a head equal to little p. Okay, someone tell me the probability of getting I heads. You've been doing this sort of thing with airplane engines and everything else over the last week. N choose I times p to the I times, yeah, and I'm going to call that q, q to the n minus I, where q is equal to 1 minus p. Okay. Now here's how to tease the expectation out of this. The first step is easy. The first step is we multiply through by the value achieved by the random variable, namely I. So we've got I times n choose I, p to the I, q to the n minus I, summed from I equals 0 up through n. Anyone can write that down, but there's a little bit of art in getting a result out of it. And I'm going to do it like this. First, what's the smallest value of I that actually contributes here? 1. Because when I is equal to 0, this kills off the term. So having rehearsed this carefully, I'm going to write my sum as running from I from 1 to infinity. Now let's write out the binomial coefficient. We've got an n factorial, which is n times n minus 1 factorial. I have an I factorial in the numerator, but this I have an I factorial in the denominator, but this I in the numerator knocks it down to I minus 1 factorial. And then I've got n minus I factorial. Everyone with me so far? I've just taken this times this. I have split off one factor of n in the numerator for reasons that will become apparent in a minute. And I've combined this with the I factorial in the denominator to just get an I minus 1. Now, there seem to be an awful lot of I minus 1s kicking around here. So let's write p to the I as p times p to the I minus 1. And then we've got q to the n minus I. The sum, thank you. Sum is only to n. Okay. Anyone want to suggest a new, possibly more appropriate index? Whoever suggests what it's equals will get to name it. Yeah, something I minus 1, what do you want to call it? J, okay. So we'll set okay. We are remarkably almost done. That's a constant, that's a constant. Neither of those depends on J. There's NP. Now we've got the sum from J equals 0, not to n, but to n minus 1, of n minus 1 factorial over J factorial times n minus j plus 1, which is actually n minus 1 minus j, isn't it? P to the j, q to the n minus j. What does that sum equal? That's the sum of the probabilities for getting j heads when you flip n minus 1 coins, summed over all the possibilities for the number of heads, and therefore that sum has to equal what? 1.
But I'm not convinced about the exponent of q.
You're not convinced about which one?
The exponent of q.
The exponent of q. You are right. What you mean is I'm wrong. N minus 1 minus j. Wait a minute. I don't like the sign on that 1, but what a...
Sign of the 1 should be a plus.
No, that's okay.
So subtracting a negative 1.
Yeah, you.
No, it's right. I'm subtracting a negative 1. So...
Let's reassure.
Oh, no. I is equal to j plus 1. So instead of subtract... So instead of subtracting I, I'm subtracting 1 and subtracting j. Okay. I could even set m equal to n minus 1, and then this turns very neatly into the sum from j equals 0 to m of m choose j, p to the j, q to the m minus j, times np, of course. And that's equal to 1. So the answer is np. And now you say, yeah, that's really pretty obvious, isn't it? When you toss one of these coins, the expected number of heads is p, the probability that you'll get a head. So I'm not at all surprised that if you flip n coins, the expected number of heads will be just n times the expected number when you flip one coin. Is there something hidden that you guys?
No. I just wanted to see.
Okay, so this is the proof done by someone who wants to exhibit skill at summing series. Here's a much more elegant proof. First, we consider flipping one coin. So if n equals 1, I will let x1 denote the number of heads that I get when I flip one coin, and that's p. It's p times 1 plus q times 0. Everyone happy with that? Okay. Now I can say, if I flip n plus 1 coins, the number of heads in n plus 1 coins is a random variable, and it's the sum of two random variables, namely the number of heads that show up in the first n coins and the number of heads that show up in the last coin. And it's always worth thinking about these and making sure that you're talking about a single sample space. An individual outcome is a collection of heads or tails showing on n plus 1 coins. But there are numerous random variables that you can define on that sample space, and a perfectly good one is the number of heads on the first n coins and the number of heads on the last coin, and surely the sum of those two random variables is the number of heads on all n plus 1 coins. That's e of x to the n plus e of x sub 1, and you have all become expert at stating simple inductive proofs. All you do now is to say, assume the result that the expectation on n coins is np by your inductive hypothesis. You can put it in there, plus p, you get n plus 1 times p. So there's an inductive proof of the obvious way of thinking about this. I got 5 minutes to do the tail sum theorem. Well, I'll give it a try. Now, this is a crazy looking result. The formula is simple, and you'd think it ought to be obvious, but it isn't. So this is the tail sum theorem, and it works only in a special but very common case where the random variable x assumes only non-negative integer values. And I'm going to use this for the geometric distribution where otherwise computing the expectation would be a real pain. Let me denote the quantity I'm calculating by a capital S. It's actually equal to the expectation, but that's what I'm trying to prove, so I don't want to write that down first. Here's what I mean by the tail sum. I do a sum from x equals 0 to infinity of what statisticians like to call the tail probability, namely the probability that the random variable x achieves a value larger than little x. Now, you might want to think of this as a tail if x is something big, like 20 or 30. You say, what's the probability that I get more than 20 heads, more than 30 heads? This is what people mean when they talk about the tail of a distribution. But it's perfectly valid even for small values of x. And now I can write this down as a double sum. I'm summing from x equals 0 to infinity, and the probability that x is bigger than little x is obtained by taking all the values that are bigger than little x, the smallest of which is x plus 1, and summing up to infinity the mass function. Everyone comfortable with this? This is the what? This is a little r, yes.
Are you doing f of r?
Oh, f of r. Thank you, Anna. Okay, everyone happy with that? And now all I have to do to prove this is write the sum in the opposite order. And as I mentioned before, I can't do this without drawing a picture. So what I'm going to do is draw a picture where x runs this way and r runs this way. X starts at 0. When x is 0, what's the smallest value of r that I use? 1. And then I use all of these. When x equals 2, the smallest value of r is hint, hint. When x equals 1, excuse me. 2, okay. And when x equals 3, which is what I mistakenly said, it's 3. And so on. So there's the set of pairs over which I'm summing. Okay, now I want to do the sum in the opposite order. What's the smallest value of r that I ever use? 1, right? And for each value of r, I sum over x, starting with the lowest value of 0. And what's the largest value of x that I use for a given r? R minus 1. F of r. I got 2 minutes, and I'm going to sneak it in here, as I'm almost done. This doesn't depend on x. I'm just adding together a certain number of copies. How many numbers are there between 0 and r minus 1 inclusive? R. So this is the sum from r equals 1 to infinity of r times f of r, which is the definition of the expectation of this random variable. So I've started from my tail sum formula, and I've shown that this is equal to the expectation. And sometimes this is a vastly easier way to compute expectation. And as soon as we resume after our break, I'll show you the classic example of that. Okay, we're back in business on topic number 6, which I have called geometric tail sum. We've already done a number of examples involving the geometric distribution. 2 of them are you keep rolling a die until you get a 6, or Fido keeps encountering the postman until Fido finally bites the postman. And I made it clear last week that the term geometric distribution is slightly ambiguous. So in this particular case, I'll do the Fido case, that the number of dog postman encounters includes the final bite, or if you're rolling a die till you get a 6, the random variable includes the 6 as well as all the preceding rolls. And I am going to denote by Q the probability that the process continues. So in the case where I'm rolling a die looking for a 6, Q is going to be 5 6. It's the probability of getting something other than a 6. Now watch how easy this is. I'll call this random variable T, and the probability that T achieves the value X is very easy to work out. If we're rolling a die until we get the probability that T is greater than X is very easy to work out. Every time I roll the die, there's 5 chances in 6 of getting something that's not a 6. What's the probability of doing that X times in succession? It's 5 6 to the X. Or, more generally, it's Q to the X. Everyone happy with that? If the dog does not bite event occurs X times in a row, then the value of the random variable has to be greater than X because Fido hasn't bitten yet. We haven't rolled our 6 yet. Okay. Now, this wouldn't be much use if we were trying to use the definition of expectation, because for the definition of expectation, we need the mass function. We need the probability that T equals X. That's a messier expression, and then I'd have to multiply it by X before summing. But the tail sum theorem says I can do it like this. The expectation of this random variable T is the sum from X equals 0 to infinity of the probability that the random variable exceeds X. I just proved that. And that's the sum from X equals 0 to infinity of Q to the X, which you all know is 1 over 1 minus Q, or 1 over P. So easily proved and easy to remember, too. What this says is if you're going to roll a die and stop as soon as you get a 6, since the probability of rolling a 6 is 1/6, then the expected number of rolls is 6. If someone is trying to make a point at blackjack and the probability that they will roll neither that point nor a 7 is, let us say, 2/5, you can say to yourself, aha, then this craps game will continue. I said blackjack when I meant craps. This craps game will continue for an extra expected 2.5 rolls until the shooter either wins or loses. That troubles people about expectation, you know. But you have to be comfortable with that. It's true, you can't roll a die 2.5 times. What you could do is say, if you're a really avid craps player and wait for this situation to show up 1,000 times, you would expect there to be about 2,500 rolls closing out the game. But there's nothing wrong with an expectation being an irrational number, say. You don't have to relate it to actual counting, and that's really one reason it's such a powerful and useful concept. Okay, now we're going to do negative binomial. I could do negative binomial the way I did binomial. That is, I could try writing down the mass function for the negative binomial distribution, multiplying through by x, and seeing whether I could manipulate the factorials until I got a series that I could sum. But that would be cruel and unusual punishment, and only the CIA should be allowed to do that sort of thing. So we'll do it the easy way. So this is number 7, negative binomial. And now let's think of the example of a negative binomial where we roll a die until a 6 appears n times. an individual outcome in this sample space is a sequence of die rolls that looks like this. We've got some non-6s and then a 6, and more non-6s and a 6, and more non-6s and a 6, and finally the nth 6. Now, random variable t is the number of rolls including all the 6s. And now I can write t is equal to t1 plus t2 plus dot 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 plus tn, where by t1 I mean the number of rolls up to and including the first 6, t2, the number of rolls up to and including the second 6, and finally tn is the number of rolls after the next to last 6 up to and including the final 6. Now, does everyone agree with me that each of these t's, t1, t2, etc., is a perfectly good random variable? It's a function from the sample space to the real numbers in the sense that given the sequence of die rolls, you can tell me, oh yeah, in that case t1 had the value 5, t2 had the value 3, and so on. But what did I prove earlier? I proved that for the sum of two random variables, the expectation of the sum was the sum of the expectations, and I could trivially extend that by induction to any finite number. So the expectation of this random variable t is the expectation of t1 plus the expectation of t2 plus dot 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 plus the expectation of tn. But now what sort of what sort of distribution did I just blurt out is obeyed by the random variable t1? It's geometric, isn't it? So each of these random variables has an expectation of 1 over p, which in the case of dice is 6. And that's n over p. So with essentially no calculation, we have figured out the expectation for a negative binomial distribution. If every dog gets 2 bites, the number of postal encounters for that dog before his second and final bite will be just twice the number that you expect before his first bite. So that's a good way of dealing with negative binomial, and this is the sort of situation that you'll now start noticing in the world around you. Lots of processes that go on are really just a succession of geometric distributions like this, and don't think, oh, that's awfully messy. You know, if I tried to write that down, the mass function has a negative binomial coefficient in it. Think, no. There's something very simple I can say about this. For each of the geometric distributions out of which this is built, the expected number of times things have to happen is just 1 over the probability of the event that stops the sequence, the 6 or the dog bite, and then I just multiply by n because there are n of them. Now, in fact, once you catch on to that reasoning, you say, why do all these things have to be the same? And after thinking about it a while, you may realize, as I did, that there's a situation that shows up all the time where you're trying to collect a set of things. And since the textbook calls this coupon problem, I'll call it coupons too. But let me tell you the situation in which I most recently encountered this. I'm trying out an online video game called A Tale in the Desert, where you go into ancient Egypt and you have to sort of craft everything you need for your world. And one thing you can do is catch fish. And I found a place where when I threw my fishing pole into the water, Sometimes I got tilapia fish, sometimes I got perch, and sometimes I got carp. And I found myself asking, how many times will I have to throw this fish pole in until I've got at least one of each type of fish so I can go and try cooking things out of them? Another scenario, I've used this on an exam problem, and I may slip up and use it on the final. A young graduate decides to try out various jobs before settling down, and resolves that he's going to try at least one job that brings him fame, at least one job that brings him lots of money, and at least one job that brings him happiness. And the probability of getting any of these benefits from an individual job is, say, 1/3. Each gives only one of these three things. And the question is, how many jobs will he expect to have to try until he's become famous once, rich once, and happy once? The standard coupon problem is cereal boxes contain, well, the current example is busts of recent presidents of Harvard. Sturzacher uses busts of vice chancellors of Cambridge University. But you know the things you get out of cereal boxes. And the temptation is irresistible to keep eating that cereal until you've got the complete set. So here's my example. My example is when you register for an extension school course, you get an email that includes a nice photograph of precisely one of 3 deans of continuing education. And you may get a Schneegel, you may get a Leitner, or you may get a Higgins. So you register for a course, and you'll get, with probability 1/3, a photograph of Dean Michael Schneegel, or a photograph of Dean Henry Leitner, who runs the computer and technical type stuff, or a photograph of Dean Mary Higgins, who's the person who gets the catalog out and makes an awful lot of decisions. And each of these has the probability of 1/3. Now you see what can go wrong. You keep registering for courses, and every time you register for a new course, you get another Schneegel. And you're not allowed to trade these things to complete your set. So you have to keep going. You might get a whole degree before you finally get that Higgins you were missing. So let's figure this out. Random variable T1. You don't have any of these decanal photographs, and T1 is the number of courses you have to register for until you get your first dean. The probability of getting a dean you don't have is p = 1. So the expectation of the random variable T1, rather trivially, is 1. Okay? This is an example of a random variable that assumes one and only one value. And you can see in this context of several random variables we're going to add together, it's useful to be able to talk about a random variable that isn't really random at all. Okay. Now, T2 is the random variable that specifies how many courses you have to register for till you get your second dean. Whether you got a Schneegel, a Higgins, or a Leitner on your first try, the probability of getting a dean that you don't already have is now what? 2/3. And therefore the expected value of T2 is, by the rule I just proved, this is a geometric distribution with Q = 1/3, P = 2/3, and the expectation is...
You threw out the probability upside.
Oh, I did. I thought these boards were supposed to explode in flames if you ever wrote a probability that was less than 0 or greater than 1. I feel lucky to have survived. Okay, so P is 2/3, and the expectation is therefore 3/2. Okay, now you've got two deans. Whichever two deans you've got, you got a probability of 1/3 the next time you register for a course of getting the third dean. So now P equals 1/3, and the expectation of T3 is what? 3. And if T is the total number of courses, that's a perfectly good random variable. The expectation of T is the sum of these three things, 1 plus 3/2 plus 3, which is equal to 11/2. So you expect to have to register for 5.5 courses in order to get one each of the three deans. Isn't that easy? So this is a situation that you'll encounter quite frequently. You're trying to complete a collection, and what you do is just say, at each stage, you have to take 1 over the probability of a successful event. Now, let me tell you, this problem can easily be made much harder, and I will get next week to the infamous tartan dice problem from the book. In the book, there is a hypothetical cubic tartan die which has 3 Scottish something or others, one of which shows up on 3 of the faces, one of which shows up on 2 of the faces, and one of which shows up on only 1 of the faces. And now life becomes much more difficult, because if you get the easy one first, then you've got only a probability of 1/2 of getting a new tartan on the next one, and you may end up in a situation where the probability goes to 1/3 or to 1/6 to the next one. So I will be returning to this example and showing you how to deal with it in cases where the probabilities aren't all equal, but we'll need conditional probability to do that. Okay, I've got 2 more things I'm determined to do, and I've got time for it. So what I'm going to do now is, because there's a problem on the homework that involves a fairly trivial computation of variance, I'm going to avoid repeating last week's mistake, and I'm going to go ahead and do the first topic on the next outline, which is called variance. And then I will go back and work the telescoping series problem that I took off this week's homework, and then I'll go on and start discussing some interesting convergence issues. So this is outline 8, number 1, variance. And I will admit that this is a topic I'm skimping on in this course. In statistics courses, a great deal of attention is paid to variance. The problem with working with variance is that calculating variance involves lots and lots of sum the series tricks, and most of the really good tricks, remarkably, involve the use of calculus. It involves the use of calculus just to get extra powers of p in there, and since there's no calculus prerequisite for this course, I don't want to teach you those tricks. So I'm going to define variance. It will show up from time to time, but I'm not going to focus on various messy problems involving variance that have long been a staple of probability and statistics courses, just because I think you would find them lots of manipulation of symbols that didn't tell you all that much. However, I will give you the formula for calculating variance, and the first thing I want to do is to define the so-called second moment of a random variable. That's just a fancy phrase meaning the expectation of x squared. Now, if a random variable has an expectation of 0, so that it's, loosely speaking, as often positive as negative, then the expectation of x squared gives you a good measure of how far away from 0 it's likely to be. So this is a standard way of measuring how spread out something is, but it only really works when the expectation is 0. So this is enlightening. If the expectation of x equals 0. On the other hand, if x only achieves values between 10 and 12, the expectation of x squared will be somewhere around 120, say, and whether it's 105 or 120 or 130 doesn't tell you very much. And that's what motivates the definition of variance.
When you say 0, Paul, could that just be anything normalized to 0? Is that what you mean?
Well, yes, that's a good way of thinking about it. You can say, given any random variable, I can make a random variable whose expectation is 0 just by subtracting off the expectation. So that's exactly what's done in calculating variance. You take a random variable x, and you subtract from it a constant, namely its expectation. Now, this is a random variable whose expectation is 0. Now you square it so that it's always positive, and you take its expectation, being sure to put in enough parentheses, and you have the definition of variance. This is written as var of x. Var is the name of a function. This is something that assigns a number to a random variable. And if you're doing the computer project, you can have a lot of fun building variance calculations into your displays of various distributions, and you'll be able to check some of the results that I prove, some you get on the homework, some you can find in our textbook that I didn't talk about, and so on. But in many ways, calculating variance by brute force on a computer is an appropriate way to proceed, because a lot of times the calculation can't be done by means of any algebra. Now, this makes it look as though when you compute variance, you should do it in 2 steps. That you should first go through and compute the expectation, having got that number, subtract it off, get this new random variable, and try again. But there's actually a way of doing this variance calculation in a single step, and here's how it works. What is this? This is a function of the random variable capital X. It's capital X squared minus 2 times the expectation of x, which is just a number, times x plus the expectation of x squared. And I proved earlier that if you have a sum of functions of a random variable, the expectation of the sum is the sum of the expectations. So this is the expectation of x squared, the second moment, minus twice the constant e of x times the expectation of 2x. That's twice the expectation of x squared. And this is a constant random variable. Its expectation is itself e of x squared. Everyone happy with that? And now a curious thing happens. These two terms are almost exactly the same, except that one has a coefficient of minus 2 and the other has a coefficient of plus 1. So that gives us the final useful formula for calculating variance. The efficient way of calculating the variance of x is to calculate the expectation of x squared, the second moment, and then to subtract off from that the square of the expectation of x. And this is built into lots and lots of spreadsheets and calculators and so on. It doesn't, in general, use actual probabilities. It uses observed frequencies, but you can calculate the mean and the variance of a set of data. And it's usually done by this formula because it can be done in a single pass. And in fact, a lot of times when people are making probabilistic models for things, we were doing this all the time in speech recognition, nobody really knows what the right model is, and they pick something that's simple and easy to compute with. And two competing models are ones that involve the exponential of minus the absolute value of x and the exponential of minus the square of x. And there's always one camp that favors the latter simply on the grounds that then what you end up computing is the variance, and you can do that on the basis of one pass through the data, whereas with anything else you have to make two passes through the data. So that's the definition of variance. And now I'm going to add in a topic that's not in the outline. So I'm going to write this up on the board. This is going back to outline 7. Number 9 is called telescoping series. And it was one of the distance learners who sent me an email over the weekend pointing out that this problem which I had assigned used the concept of expectation. Rather trivially, but it used it nonetheless. And then I looked at the problem and thought, I think that problem's cute. But I think it's cute because I know how to do it. How many of you succeeded in doing this one? Okay, about what I've got. How many of you beat your head against the wall for a while and gave up? Wow, well, okay. So maybe I'm preaching to the choir here, but I will show you my solution to the problem. This is an absolutely standard trick, but I think trick is the appropriate word. This is a way of getting mass functions for which you can actually calculate the expectation. And this is the simplest example where you can actually compute the expectation. So here's the idea. We have a mass function which is some constant c over x times x plus 1 times x plus 2. And if you wonder, why that? Why didn't you just put x cubed there? The answer is because you can do the arithmetic in this case. And I don't think you can make a case, oh, this one shows up in the real world, whereas the one with x cubed doesn't. I think the answer is because in this case, we can use a cute trick, and here's the cute trick. I can write this thing as the difference of two fractions. And unless you know the trick, you're unlikely to think of it. And I didn't think the answer in the back of the book gave a particularly good hint, though the closely related worked example did sort of put you on the right track. So what I'm going to do is write this in terms of two fractions. One will have the denominator x times x plus 1. The other will have the denominator x plus 1 times x plus 2. And when I put these over this common denominator, I'll have an x plus 2 here minus an x here. That will give me an extra 2 that I have to get rid of. And therefore, I can write this as c over 2 divided by this minus c over 2 divided by that. When I add these two fractions, I multiply this by x plus 2 and this by x in order to get them over a common denominator. X plus 2 minus x gives me 2. That kills off the 2 I have here. Okay, now I have to figure out the value of c. What criterion determines the value of c? The whole thing sums to 1. So let's sum this up. the sum of this mass function is the sum from x equals 1 to infinity. I better not start at 0 because then I'd be dividing by x here, of c over 2 divided by x times x plus 1 minus c over 2 divided by x plus 1 times x plus 2. And now I can sum these terms and these terms individually. So this is the sum of c over 2 times x plus 1 from x equals 1 to infinity minus the sum, I'm getting ahead of myself, from x equals 1 to infinity of c over 2 times x plus 1 divided by x plus 1 over x plus 2. Now these two sums are remarkably similar, aren't they? In fact, they become almost identical if I rewrite the second one by introducing a new index of summation, which is x plus 1. Let's call it y, as we were doing earlier this evening. And so y runs from something to infinity, c over 2 times y over y plus 1. But what is the lower limit on y here? If x runs from 1 to infinity, y goes from 2 to infinity. Now, at this point, I could change the name back to x. It's always difficult to know which is the less confusing way of doing things. I slightly prefer this because if I change this back to x, I'm suddenly going back to using x to mean what was called x plus 1 just a minute ago. And that gets kind of confusing. So here's a set of terms going from 2 to infinity. Here's a set of the same terms going from 1 to infinity. How many terms survive when you put it all together? Just one. So this is equal to the sum from x equals 1 to 1 of c over 2 times x plus 1. And that's equal to c over 4. That's equal to 1. So c equals 4. So far, so good? Now, the book actually posed a harder problem first. The book poses first the harder problem, what happens if you only run up to m? So let me do that one. And because I've done so much work here, this is ordinarily bad practice, but with this much messy arithmetic and unscheduled topic, I'm going to do some proof by erasure.
One question.
Yes, sure.
How do you know that the x's are all integers?
You're told that. You're told this is the mass function for all integer values of x. The probability that this random variable will achieve a non-integer value is 0. It can only achieve the values 1 through infinity or through m inclusive. Are you looking at the statement in the book, Sue?
Yeah, I'm looking at the problem.
Okay, and it's not clear from that?
No, it just says 1 is less than or equal to x, less than or equal to m.
Yeah, that's...
It never says it's an integer.
It's funny. If he'd said 1 is less than I is less than or equal to m, that conveys a strong hint that the values are all integers, whereas the use of x is a little bit misleading. But that's certainly the assumption.
Was the intent.
And by proof will be I'm going to get the same answer he does by making that assumption. So I'm going to go back without recopying everything and change all the upper limits to m. This makes a significantly harder problem, but we can do it. The reason it's a significantly harder problem now is that we've got the sum from x equals 1 to m of c over 2 divided by x times x plus 1 minus, now I'll change my index of summation to y again. From y equals 2 to you figure out what? Y times y plus 1. And as x goes from 1 to m, the new index, y, which equals x plus 1, goes from y equals 2 up to y equals m plus 1. Okay. Now you think about this a bit, you say, oh yeah, most of the terms cancel, but there's one extra term at the beginning here and one extra term at the end here. And this is a general warning about problems that are done by summing series. Very often, the crucial step is getting the limits on the summation just right. And if you go from 0 to infinity when you should have gone from 1 to infinity, you get the whole thing wrong. And therefore, this is a very touchy calculational issue, which you may or may not want to aspire to excel at. Okay, what have we got here? We got c over 2 divided by 1 times 2. And then we've got the one leftover term here for m plus 1, which is c over 2 divided by m plus 1 times m plus 2. And when I added those fractions, I got the right answer. I got c over 4 times 1 minus two over m plus 1 times m plus 2. Okay. So far, so good. There's my c over 4. And I've got a c over 4 out there, so I've got a 2 there. And let's see. Emily, you've got a clear view of this, so I can go one line down. This is equal to c over 4 times, let's put it all over a common denominator, m plus 1 times m plus 2 minus 2 over m plus 1 times m plus 2. And that whole business has to equal 1. So that's my answer. C is equal, believe it or not, to 4 times m plus 1 times m plus 2 divided by, flip this over, so I have to move this numerator to the denominator, that's m squared plus 3m plus 2 minus 2, which factors very neatly into m times m plus 3. Now, this calculation was probably enough reason for me to withdraw the homework problem, but the reason I actually withdrew it was because it asked to calculate an expectation before I had talked about expectation in class, and that will now turn out to be the easy part of the problem. So let's calculate the expectation of this. Once we know the value of c, getting the expectation is pretty straightforward, and the reason is, to compute the expectation, you multiply by x before you sum, and here we conveniently have an x in the denominator. So the expectation of this variable is the sum from x equals 1 to infinity of x times my mass function. And that's the sum of c divided by x plus 1 times x plus 2 from x equals 1 to infinity. Now, that one is really easy to write out because 1 over x plus 1 times 1 over x plus 1 over x plus 1 times x plus 2 can easily be written as the difference of two fractions. This is c over x plus 1 minus c over x plus 2. Everyone happy with that? And now this poses an interesting problem. Can anyone tell me what this sum equals with just this term? It doesn't exist. It's infinite.
The harmonic.
It's the so-called harmonic series. It's the sum of the inverses of the integers. So, strictly speaking, I have no business writing this like this. In the sense that if I ask my computer, first calculate this, then calculate that, the computer will say, both those sums are divergent. Neither this nor this makes any sense. However, if I put the terms in this way, it's quite easy. Because what have I got? I've got a c over 2 minus c over 3. And then the next time I get a plus c over 3 minus c over 4, plus c over 4 minus c over 5, and so on. And I can cancel these pairs out in order. So this is your first example of a so-called conditionally convergent series. This is a series that makes sense only if you sum the terms in the order specified, and rearranging them like this in general produces a different result and is something that you should avoid. And on the other hand, it's perfectly easy to see what's going to happen here. If you keep going, all the terms are going to cancel themselves out. And you'll get just c over 2, which is 2. The right way to do this is the way that Sturzacher suggests. Namely, first you do it for some fixed capital M. Now you're only summing a finite number of terms, so you can't get into any trouble. And then after you've done that, you let M approach infinity, and you will get the right answer. And I guess I've got just time for one more example. I've got 10 minutes or so. So I'm now going to go back to outline number 8 and do curious topic 2, convergence. This is slightly off the record because I'm going to have to drag out some famous curious results that you may or may not have seen before and come up with a highly contrived example where it looks as though a random variable has a very cleverly calculated expectation, and in fact the whole thing is nonsense. So here is topic 2. This is outline 8, number 2, called convergence. And here are the preliminaries. Anyone know what that sum equals? Pi over 4. This is known as Gregory's series. Who therefore was not the first person to discover it? Gregory. It was in fact first discovered in Kerala in southwest India, and the sum is generally attributed to an Indian mathematician named Nilakantha, who worked about a century before the Europeans who pioneered this subject. So this is Gregory's series. Probably discovered by Nilakantha. The next one is more curious. 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus dot, dot, dot. This one stumped generations of Bernoullis. There are all sorts of famous mathematical Bernoullis, and none of them could sum this. This was finally summed by Euler in the late 18th century. Anyone know his answer?
Pi squared over 6.
Pi squared over 6. And Euler, in fact, summed this by an outrageous trick. It gave him the right answer, and the trick was so outrageous he couldn't convert it into a proof. When challenged by his contemporaries to prove it, he finally, 10 years later, came up with a completely different line of reasoning that led to a rigorous proof. Okay, now I'm going to do something weird with this. I'm going to divide it by 4. And I should say, when all the terms in a series are positive, you don't have to worry about convergence. The ones that can do you in are cases where some of the terms are positive and some of the terms are negative. So this is all strictly legit. I'll divide this series by 4. The 1 divided by 4 gives me 1/4. The 1/4 divided by 4 gives me a 16th. The 1/9 divided by 4 gives me a 36th, and so on. And therefore, pi squared over 8, which is pi squared over 6 minus pi squared over 24, is equal to 1 plus 1/9 plus 1/25 plus so on. Euler figured this one out almost immediately after figuring that one out. And this little result is going to let me calculate the normalization constant for a random variable in a curious game of chance. So I'm now going to save this result. Pi squared over 8 equals 1 plus 1/9 plus 1/25 plus dot, dot, dot. I need this whole board to describe our little game. So here's a game of chance. We play this game, certain results come up with certain probabilities, and the payoff is how much I pay you. One possible value for this payoff is 1. And that's going to happen fairly frequently. It's going to happen with probability 8 over pi squared, which is nearly 4/5 of the time. So roughly 8/10 of the time, you're going to win $1 from me. But sometimes you're going to have to pay me $3. So this is a random variable that can assume negative as well as positive values. And the probability of that is 8 over pi squared times 1 over 3 squared. And sometimes you will win $5. That will happen with probability 8 over pi squared times 1 over 5 squared. Sometimes you'll lose $7. That'll happen with probability 8 over pi squared times 1 over 7 squared. And now you can calculate the sum of the mass function, which is 8 over pi squared times 1 plus 1/9 plus 1/25 plus dot, 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 which is equal to 1, because Euler proved that this series sums to pi over 8.
You didn't make explicit that those payoffs just keep going like that.
The payoffs keep going, yeah. And on the other hand, already for this one, the probability is getting mighty small. We're down around 1% for this. So large payoffs are quite infrequent. Nonetheless, they are frequent enough so that the expectation is undefined. So here's the weird thing about this example. Now, first let me show you the phony calculation. You can take in most amateur mathematicians in the world with this one. The sum of x times the probability that the random variable x achieves the value little x is equal to what? Well, it's 1 times this. So it's 8 over pi squared times 1. And then I have to take this and multiply by minus 3. So I have minus 3 times 1 over 3 squared. That's minus 1/3. And down here, the payoff is 5 to u. I multiply by 1 over pi squared and get 1/5. And down here, the payoff to u is minus 7. I've got this 1 over 7 squared. So it looks as though this is equal to 8 over pi squared times pi over 4, which is equal to 2 over pi, and that this would be a fair game if you pay me 2 over pi dollars to play it. Okay? This is a phony argument, but does everyone see why someone might believe it? It's a phony argument because this is a so-called conditionally convergent series. When we say this is equal to pi over 4, what it means is you take a computer, start with 1, subtract a third, add a fifth, subtract a seventh, add a ninth. That computer program will alternately generate numbers that are a little bit bigger than pi over 4 and a little bit smaller than pi over 4, and they'll get closer and closer together, and they will squeeze pi over 4. This is the standard way of defining what pi over 4 means. That's not the concept of infinite series that we need for calculating expectation, because in that formula for expectation, there's no indication of what order you sum the terms in. Basically, you throw them all in together, and if the answer isn't unambiguous, it's meaningless. But you can't impose any ordering on the terms. And that's what Sturzacher means when he says all the series have to converge absolutely. Conditionally convergent series, which are great fun, have no place whatever in probability series and probability theory because there's no natural ordering of the terms. So this is rubbish. Now, I'm going to give you 2 quick explanations of why it's rubbish. Let's compute the expectation of x squared. That's a preliminary step in computing the variance. And this is very easy to do because it's the sum of x squared times the probability that capital X assumes a certain value. And that's 8 over pi squared. Now for the first term, x squared is 1. And then for the next term, x squared is 9, but the probability that x was equal to minus 3 was 1/9. So I get minus 1. I get plus 1. So when I go to compute the expectation of x squared, I just get an infinite sequence of 1s, which means the variance and the second moment are not defined for this variable. I've got 5 minutes left, but I don't need that much. And usually this happens in these cases where it first looks as though you can compute an expectation, but just barely. You calculate the variance and discover that the series diverges. There are perfectly respectable probability distributions for which the variance diverges, but this is not one of them. Now I want to explain to you in real-world terms why this is a phony. Let's suppose I change the rules of the game very, very slightly. I say, yeah, I'm happy to play this game with you, and in fact I'll play it for free with you, but I know that you expect to win a little bit of money out of me every time. So to even things up, why don't we say this? If you should win more than $1,000 from me, I'll give you $1,000, but we won't impose that rule on your losses. So you can lose an arbitrarily large amount to me, but you can't win more than $1,000. And you look at this and say, yeah, probability of winning or losing $1,000 is down in the tiny fractions of a percent. That can't possibly make any significant change. But let's try it now. So the new random variable, whose expectation we want to calculate, is the expectation of the smaller of x and 1,000. Right? The deal is you can't win more than $1,000. So whatever winning comes up for you, we'll take that number or 1,000, whichever is smaller. Now what are we going to get? So this is the expectation of this business. And what's that equal to? Well, there are lots of terms that are the same as before. 8 over pi squared times 1 minus 1/3 plus 1/5 minus 1/7. And this will keep on going out until we get, I think, minus 1 over 999, though I'm not quite sure whether that's a plus sign or a minus sign. And then we've got a bunch more terms. We've got all the terms where you would have won more than $1,000, except you made a deal with me that you didn't have to pay me more than that. So you've got plus 1,000 times 1 over 1,001 plus 1 over 1,001 squared, 1 over 1,005 squared, plus 1 over 1,007 squared, plus dot, dot, dot. And then there are all these terms where you lose a lot, and that's minus 1 over 1,003, minus 1 over 1,007, minus 1 over 1,009, and so on. So all of this gets multiplied by 8 over pi squared, but it doesn't make much difference. Okay, this is finite. What can someone tell me about this sum? Sum of inverse squares starting at some point. Converge or diverge? No. If they're all positive, it may converge, it may diverge, but the result can't depend on the order. But the general rule is when you're summing or integrating with a square in the denominator, it always converges. So this converges. What about this one? This has first powers in the denominator. I guess this should be 10, 11. So this is the sum of lots and lots of negative numbers, and this one diverges. That is, you keep adding on enough terms of this, you can make it as large as you like. So with this modified version of the game, where you can lose arbitrarily much, but you can't win more than $1,000, what's your expectation?
Sure.
It's negative infinity. And curiously, no matter where we set this limit, even if I say, there's no way I'm going to let you win more than $1 million from me, that's the only rule change we make, the expectation is still negative infinity. Whereas if you say, hey, no, why don't we do it so that I can't lose more than $5,000, then your expectation is plus infinity. And it's because the expectation is so sensitive to this subtle change in the rule that the only sensible thing to say about this game is its expectation is undefined. We have no business applying the concept of expectation to this game. Okay. So the general rule is if you write down a series that you think computes an expectation and the series is only conditionally convergent, it converges only because of an alternation of plus and minus signs, and the result depends on how the terms are ordered, you say, sorry, that series doesn't mean anything in the context of computation of expectation. The expectation isn't defined at all. Okay, curious example, and next week I've got one more slightly less curious example, and then we'll get back to more straightforward stuff. But I just wanted to point out, for the benefit of those of you who've studied conditionally and absolutely convergent series in the past, that the topic is actually highly relevant to the subject at hand.